Hi everyone! In this video we're going to go over a different type of preparation of amines called reductive amination. So in this method we're going to start with a ketone or aldehyde. And we're going to add catalytic acid, ammonia, and we're also going to see the loss of a water molecule, so we'll just write that in parentheses. And this will give us something called an iminium ion. So you might remember this from previous lectures. Now, once we have this iminium ion, what we can do is reduce the double bond between nitrogen and carbon, and that will give us a primary amine in this case. But what we'll see later on is we can also create secondary and tertiary amines using this method. So in brackets above the arrow, I'm just writing RED for reduction. So what type of reducing agents do we know that could reduce the iminium ion to an amine? So you might be thinking about lithium aluminum hydride or sodium borohydride. And while we have used those in the past, here they're not really going to work because they're actually going to react with the ketone or aldehyde first. So let's just make a note. So using lithium aluminum hydride or sodium borohydride as the reducing agent, will reduce the ketone or aldehyde. But we want to reduce the iminium ion, not the ketone or aldehyde. So we need something different. So let's just write down here that if we do use, let's say, sodium borohydride as part of our reaction, we're going to end up with an alcohol. And we're trying to create an amine, right? So what we need is an even gentler reducing agent than sodium borohydride. So remember, if we rank our reducing agents, lithium aluminum hydride is stronger than sodium borohydride. So we need something that's even gentler. So the reducing agent we're going to use for this reaction is called sodium cyanoborohydride. So notice that this looks really similar to sodium borohydride, but we've replaced one of the hydrogens with a nitrile group, so the CN group. And let's just write the name down here, sodium cyanoborohydride. Okay, so let's draw what that looks like. So we still have 3 hydrogens attached to boron, but one of those is now, or I guess the 4th hydrogen is now a cyanide group, or a cyano group. So boron is negatively charged since it's bonded to 4 different groups there, and sodium is going to balance that negative charge. Now, why is this reducing agent weaker than sodium borohydride? Why does that carbon-nitrogen group make a difference? Well, remember that cyano group is an electron withdrawing group. So that's going to reduce the strength of our hydrogen atoms as hydride groups. So this electron withdrawing group makes reduction slower. Now, the great thing too about this reducing agent is it will not reduce ketones or aldehydes. So this will only reduce, for instance, that aminium ion or an imine, for example. So this is a perfect reducing agent for what we're trying to do. Okay, so let's summarize. Let's start with a ketone, but remember you could also start with an aldehyde. And we said that if you add catalytic acid and ammonia, followed by sodium cyanoborohydride, you're going to end up with that primary amine. But earlier I also mentioned that we could create a secondary or tertiary amine as well. We just have to change that nitrogen molecule that we're using in our reagents. So for instance, if we change ammonia to a primary amine, and then again we're using that sodium cyanoborohydride. Oh, whoops, not 4 hydrogens, 3. This is going to give us a nitrogen on the top here that has 1 alkyl group attached. So now we have a secondary amine. So our first one was a primary amine. Now we formed a secondary amine. And you can probably guess that if we use a secondary amine in our reagents, we're going to end up with a tertiary amine in our products. So this is a really useful reaction that we can do, this reductive amination. We saw previously that, for instance, Gabriel synthesis can be used to produce primary amines. But what if we do want to create a secondary or a tertiary amine? Well, with this reductive amination, we can have better control over the type of product we have. Let's look at a pharmaceutical example of how we could use reductive amination. So let's say we're starting with this molecule here. We can use reductive amination, and the amine we're using has a methyl group attached. Well, I drew that kind of in the wrong order, but you get the idea. There's a methyl group here. And we're again using that sodium cyanoborohydride. So most of the molecule stays the same. But our ketone, is now an amino group. Or not an amino group, but an amine. And it has a methyl group attached. Now, this structure is commonly known as Zoloft. And this is what's used as an antidepressant. Now, notice that the structure here has two stereocenters. The one on the bottom, that's a wedge, that will stay the same, but the stereocenter on the top is going to be either R or S. So we actually end up with a racemic mixture. Okay, so let's also practice a synthesis problem, but we're going to kind of work backwards. So let's say that we're given an amine and we have to figure out what we started with. So I'm going to give you the following. And I would like you to figure out what did we start with. And remember, we just saw on a previous slide here that we should probably start with either a ketone or an aldehyde, and then we would use catalytic acid, some sort of amine. It could be primary, secondary, or ammonia. And I want you to try to figure out what did we start with to make this product here. So you can pause the video, try this on your own first, and then we'll go over it together. Okay, so probably the easiest thing to do, if we look back at our, oops, there we go. If we look back at our previous slide here, notice that what we're doing is really adding, for instance, NH2 from ammonia to this spot where oxygen is. And instead of a double bond, we'll end up with a single bond between carbon and nitrogen. So maybe what we could do is kind of chop that bond between carbon and nitrogen in half. And on one side would be our ketone, and on the other side is our original amine. So let's go back here, and let's just pick one of these bonds. It doesn't really matter which one we break because they're all valid. So let's just pick this one to the right. So on one side, we would have our amine. And on the other side would be our ketone or aldehyde. Although in this case, this carbon that I'm circling on the product, it doesn't have any other alkyl groups attached, so that would probably be an aldehyde. Now, if we want to clean it up a little bit, we can just rotate some of our bonds. So let's see, we've got 1, 2, 3, 4 carbons. So 1, 2, 3, 4. So that would be our starting material. So we've got our amine on one side and then our aldehyde on the other, and this would be an intramolecular reaction. So the reagents that we would use if we go in the forward direction, we would use that catalytic acid and then sodium cyanoborohydride. Okay. So let's summarize everything we've learned so far about how to prepare amines. So let's say that our ultimate goal is to make a primary amine. So let's just draw a primary amine. There are multiple ways to do this, as we've seen. We could start with an alkyl halide, and we could also start with an amide. We could start with a nitrile, an aldehyde, or a ketone. I'll just draw an aldehyde. Or we could start with that phthalimide, right? Okay, so see if you can figure out the reagents for these different reactions. So pause the video, go back over your notes, fill in the blanks, and when you're done, we'll go over it together. Okay, so if we start with an alkyl halide, what we could do is use sodium azide, so that's NaN3, followed by lithium aluminum hydride, or you could also use hydrogen and platinum, or hydrogen and palladium mixed with carbon. That works too. And then we'll follow that with water. What if we're trying to convert an amide to a primary amine? What would we use? Lithium aluminum hydride again, followed by water or acid. What about our nitrile? Same thing, right? We would just reduce it. What if we have an aldehyde or a ketone? Well, we just saw with reductive amination that we can use catalytic acid, ammonia, and then sodium cyanoborohydride. And then finally, what if we start with Gabriel synthesis? So we have phthalimide there. Well, we would first want to deprotonate the nitrogen. So we would need a base like sodium hydroxide or potassium hydroxide. And then we'd follow that with an alkyl halide. And then we could use either acid or hydrazine. Okay, so once we have our primary amine, what if we wanted to make a secondary amine? What reagents could we use? Well, we could do reductive amination again, but we're just using, oh, sorry, I don't know why I put an extra carbon in here. There we go. Still just an R group. So we're going to use reductive amination, and we're going to use the primary amine as one of our reactants. But remember, we also need an aldehyde or a ketone. So we could just use, let's say, an aldehyde. And again, we'll use sodium cyanoborohydride. Now, what if once we make our secondary amine, we want to then convert that into a tertiary amine? Well, we could use reductive amination again. So I'll just write reductive amination since I'm running out of room. So this is really cool, right? Because maybe we don't have any amines handy, so we could start with an aldehyde and ammonia and then make our primary amine. And then we can use the primary amine that we synthesized along with reductive amination to then make a secondary amine. And then we could go a step further and make a tertiary amine. So lots of tools in our tool belt now. All right, so we'll stop here for today. Next time, we're going to discuss the reactivity of amines. So we'll talk about acylation of amines, and then we'll start discussing other reactions that we can do with amines as well. So I will see you then.